The images arrived overnight, downloaded from observatories across 3 continents, processed by NASA's imaging teams, released to the scientific community with notes attached highlighting features that shouldn't exist. 3. I-Atlas, the interstellar visitor that's rewritten expectations repeatedly, and the latest photographs show it's doing it again. Change is visible to the eye even without detailed analysis. Transformations occurring over days that models predicted would take weeks or never happen at all. Expanded coma, new jets appearing where surface was dormant. Color shifts indicating chemistry that doesn't match any solar system comet. Structural modifications, suggesting forces operating beyond what thermal physics predicts. This isn't interpretation. This is direct observation. Multiple facilities imaging the same object at the same time, reaching identical conclusions. Ground-based telescopes in Chile's Atacama Desert. Subaru Observatory atop Mauna Kea in Hawaii. Facilities in China's high-altitude sites, and, coordinating from above, Hubble Space Telescope and James Webb, adding resolution and spectroscopic detail that ground observations cannot provide. The consensus is unanimous. 3. I-Atlas has transformed, and the transformation defies standard cometary physics in ways that demand explanation. These are the first clear observations since solar conjunction ended. For weeks, the comet passed too close to the sun's glare for imaging. Telescopes couldn't track it. During that gap, something happened. And when visibility returned, photographers found an object that looks fundamentally different from what disappeared behind solar glare. This is the story of what those images show, what changes occurred, why they matter, and what scientists are preparing for as 3I-Atlas continues demonstrating that visitors from other stellar systems don't follow local rules. Understanding the significance of these images requires comparing them to earlier observations. Before conjunction, 3I-Atlas showed steady but unremarkable appearance for an active comet. Diffuse coma, faint tail. Jets visible but not spectacular. Color relatively neutral. Nothing that would stop a planetary scientist mid-analysis. The new photographs tell completely different stories. First change, coma expansion. The cloud of gas and dust surrounding the nucleus has grown substantially. Not gradually over weeks as thermal models predict, suddenly, as if internal reservoirs that were sealed abruptly vented. Measuring coma size requires careful analysis. Light from the nucleus blends with light scattered by surrounding material. Determining where coma ends and background begins involves statistical techniques. But even without precise measurements, the visual difference is obvious. The coma is larger, significantly larger, extending farther from the central condensation than it did weeks ago. This expansion indicates massive material release. Gas molecules escape the nucleus at speeds determined by temperature. Those molecules drift outward, carrying dust particles. The more material released, the farther the coma extends before density drops below detection thresholds. Calculating the expansion rate and working backwards reveals production rates. How many molecules per second are escaping? The numbers exceed previous measurements substantially. 3. I-Atlas is outgassing more vigorously than before conjunction, despite being farther from the sun, where cooling should reduce activity. Second change, new jet structures. Jets are collimated streams of material erupting from specific locations on the nucleus. They form when active regions on the surface release gas preferentially in certain directions. Rotation carries active regions into and out of sunlight. Jets turn on and off. Orientations change as the nucleus spins. Earlier images showed jets expected features for active comets, but the pattern was relatively simple. A few dominant jets, stable orientations, brightness variations correlated with rotation. New images reveal different jet patterns, additional jets appearing where none existed before, changes in orientation that don't match predictions based on earlier rotation periods, brightness variations suggesting some jets intensified while others faded. This indicates surface changes. Either new active regions opened, perhaps through fracturing that exposed subsurface ice, or existing active regions altered their output, possibly from changes in near-surface structure or composition. Third change, color transformation. This is perhaps the most striking feature visible in the photographs. 3. Eye Atlas appears noticeably bluer than it did before conjunction. Color in astronomical images comes from combining observations through different filters: blue filter, green filter, red filter, infrared. Each filter passes specific wavelength ranges. Comparing brightness in different filters reveals an object's color. For comets, color indicates chemistry. Dust tends to make comets appear reddish or neutral. Ionized molecules produce blue emission, carbon monoxide ions, certain carbon radicals. Finding intense blue means these species dominate the coma's light output. 3. Eye Atlas new blue appearance suggests either the chemistry changed, new molecules are being released, or ionization intensified dramatically, turning more neutrals into ions that produce blue emission. Spectroscopy is needed to determine which molecules cause the blue color. But even without spectroscopic confirmation, the visual blue indicates significant chemical changes. The comet isn't releasing the same mix of materials it was before conjunction. Fourth change, structural hints. This is subtle, requires careful comparison between before and after images. But some researchers analyzing the photographs note asymmetries in the coma, features that might indicate the nucleus isn't perfectly spherical, or that material is being released preferentially from certain regions. In extreme cases, such asymmetries could indicate fragmentation, the nucleus splitting into multiple components, each piece developing its own mini-coma. The overall appearance becoming elongated or showing multiple condensations. Current images don't definitively show fragmentation. The nucleus isn't clearly split, but the asymmetries raise the question: is 3I Atlas structurally intact, or did stresses during perihelion cause partial fragmentation that is becoming visible as components separate? Higher resolution imaging will answer this. Hubble can resolve features that ground-based telescopes cannot. If fragmentation occurred, Hubble will detect multiple nuclei. If the comet is intact, the asymmetries must come from uneven outgassing rather than structural splitting. Comment below. Which change surprises you most: coma expansion, new jets, blue color, or potential fragmentation? The changes documented in these photographs are problematic because they violate predictions. Cometary physics, built on decades of observations, says that at 3I Atlas current distance and trajectory, certain things should happen and others shouldn't. Activity should decline as the comet moves away from perihelion. Solar heating drives sublimation. Farther from the sun means less heating, which means less sublimation. Coma should contract. Jets should weaken. Production rates should drop. Instead, the opposite occurred. Activity increased, coma expanded, new jets appeared, production rates rose. The comet is behaving as if it's approaching the sun rather than receding. This requires energy sources beyond solar heating. Either internal processes generate heat, or exotic chemistry releases energy through reactions or mechanisms we haven't considered are operating. The color change is equally problematic. Blue emission from ionized species requires ultraviolet radiation to break molecules apart and strip electrons. Farther from the sun means less ultraviolet flux. Ionization should decrease. Blue emission should weaken. Instead, blue intensified. Either the ionization efficiency increased somehow, or the chemistry changed so that molecules producing blue emission became more abundant, or both effects combined. The new jet patterns don't match simple rotation models. If jets result from active regions coming into sunlight as the nucleus spins, then jet orientations should follow predictable patterns. The rotation axis is fixed in space. As the comet moves along its orbit, viewing geometry changes, but rotation continues, producing jets at consistent intervals. The observed jet changes suggest either the rotation state altered perhaps from torques caused by asymmetric outgassing, or new active regions opened unpredictably, breaking the connection between rotation and jet appearance. Each anomaly individually might have explanations. Combined, they create a profile that doesn't fit standard cometary models. 3. I-Atlas isn't behaving like a normal comet, responding predictably to solar heating. It's demonstrating behavior that requires revising frameworks or admitting that interstellar objects operate under different rules. What makes these observations bulletproof is independent confirmation. Not just one telescope reporting unusual features, multiple facilities using different instruments and different techniques reaching the same conclusion. Ground-based observatories provide the foundation. Large aperture telescopes collecting light from faint objects. Imaging through multiple filters documenting colors. Spectroscopy analyzing molecular emissions. Time series observations tracking how features change night to night. European Southern Observatory's very large telescope in Chile's Atacama Desert captured high-resolution images showing coma structure and jet morphology. The telescope's adaptive optic systems correct for atmospheric turbulence, producing images with sharpness rivaling space-based observations. Subaru Observatory in Hawaii contributed wide-field imaging documenting the full extent of the coma and tail. Subaru's large mirror collects enough light to detect faint outer regions where material density is low, but structure remains visible. Facilities in China added observations from different longitudes, filling gaps when Chilean and Hawaiian sites experience daylight. Continuous coverage requires global coordination. When one observatory sees sunset, another sees nightfall. Together, they maintain surveillance. Space-based observatories add capabilities impossible from ground. Hubble Space Telescope provides ultraviolet imaging that Earth's atmosphere blocks. Ultraviolet observations reveal hydroxyl radicals and other species invisible in visible light. Hubble's resolution resolves structures that ground-based telescopes blur. James Webb Space Telescope contributes infrared spectroscopy. Webb sees molecular vibrations that visible light spectroscopy misses. Carbon dioxide, water, methanol, organic compounds. Webb's sensitivity detects species present in low abundances that other instruments cannot measure. When all these facilities independently report coma expansion, when multiple spectrographs detect increased emission, when different cameras capture new jets, the observations become incontrovertible. This is real, not artifact, not error. Physical changes occurring in 3I Atlas that every instrument confirms. Subscribe now, because what these telescopes observe next could reveal whether 3I Atlas behavior is temporary or if the comet will continue surprising us for weeks to come. The critical unknown is what happened during conjunction. Solar conjunction occurs when an object passes near the sun from Earth's perspective. Observing becomes impossible. Telescopes can't point that close to the sun without risking damage from scattered light and heat. For 3I Atlas, conjunction lasted weeks. Last clear observations came in mid-October. First clear images after conjunction arrived in early November. During that gap, the comet was invisible to Earth-based instruments. Whatever transformations occurred went unwitnessed. Perihelion, closest approach to the sun, occurred during this gap. 3I Atlas reached minimum solar distance when nobody could observe. This is unfortunate timing, but unavoidable. Orbital mechanics determines when perihelion occurs. It can't be rescheduled for observational convenience. Perihelion represents maximum stress. Solar heating peaks. Temperature gradients maximize. Thermal expansion strains the nucleus. If structural weaknesses exist, perihelion is when they fail. Fractures propagate. Internal pressure vents explosively. Fragmentation can occur. Any of these events could produce the changes now observed. Massive outgassing from sudden venting, new jets from fractures opening, chemical changes from fresh surfaces exposing interior materials, color shifts from altered ionization conditions. But without observations during perihelion itself, confirming these scenarios is difficult. Scientists infer what happened by comparing before and after states. The nucleus was intact before. It appears changed after. Something happened in between. But exactly what remains uncertain. Some missions have captured perihelion passages. Spacecraft accompanying comets recorded detailed data throughout closest approach. Rosetta at Comet Churyumov-Gerasimenko watched perihelion from close range, documenting how the comet responded to peak heating. But 3I Atlas has no spacecraft escort. It's an unannounced visitor discovered too late for mission planning. All observations come from remote telescopes, and conjunction created a gap in coverage exactly when the most important events occurred. Future interstellar visitor studies should account for this. Planning observations to minimize gaps. Coordinating with spacecraft positioned where Earth-based facilities lose visibility, ensuring continuous coverage throughout critical phases, including perihelion. For 3I Atlas, reconstruction relies on before-after comparison and theoretical modeling. What perihelion conditions could produce observed changes? Which scenarios fit multiple lines of evidence? Which can be ruled out by contradictory data? This analysis is ongoing. Researchers are developing simulations incorporating 3I Atlas specific properties, testing different nucleus structures, varying compositions, applying perihelion heating, and calculating responses, comparing predicted outcomes to actual observations. Eventually, probable scenarios will emerge, not certainty, but constrained possibilities. And those possibilities will inform understanding of how interstellar comets respond to solar system environments. Based on current observations, researchers have identified several possibilities for 3I Atlas near-term evolution. Monitoring focuses on detecting these scenarios if they occur. First possibility, continued activity enhancement. If whatever triggered the post-conjunction changes remains active, material release might stay elevated. Coma could expand further. Jets might brighten. Spectroscopy could detect increasing production rates. This would indicate sustained processes rather than transient perihelion response. Perhaps internal heat sources remain vigorous. Perhaps chemical reactions continue releasing energy. Perhaps structural changes open pathways for long-term venting. Extended activity would provide observation opportunities. More spectroscopy characterizing chemistry. More imaging documenting evolution. More astrometry refining non-gravitational acceleration measurements. Second possibility, Fragmentation progression. If the nucleus sustained damage during perihelion, delayed fragmentation could occur. Components that were fractured but still touching might separate as rotation, and outgassing provides separation forces. Fragmentation would be visually obvious. The single bright condensation representing the nucleus would become multiple condensations. Each fragment would develop its own coma. Tracking their separation reveals pre-split rotation and constrains nucleus structure. Hubble is ideally suited for detecting fragmentation. Its resolution can separate components meters apart at 3i atlas distance. Daily imaging would capture separation dynamics. Spectroscopy comparing different fragments would reveal compositional differences if the nucleus was layered. Third possibility, return to quiescence. Perhaps the post-conjunction changes were perihelion specific. Perhaps enhanced activity was temporary response to peak heating and will now decay. Perhaps 3i atlas will fade toward predictions as it continues outward. This would be scientifically valuable despite being less dramatic. It would indicate that the anomalies were triggered by perihelion stress rather than intrinsic to 3i atlas throughout its journey. Comparing peak activity to background levels constrains volatile reservoirs and sublimation mechanisms. Fourth possibility, new surprises. 3. I-Atlas has consistently exceeded expectations. Perhaps phenomena not yet considered will emerge. Perhaps chemistry will reveal additional unknown compounds. Perhaps interactions with solar wind will create unusual structures. Perhaps the comet will do something no one predicted. Maintaining flexible observation programs ensures readiness for unexpected events. Rapid response protocols allow reacting to transient phenomena. Coordination among facilities enables comprehensive coverage when something interesting develops. These photographs of 3i Atlas matter beyond documenting one unusual comet. They inform understanding of interstellar objects generally. They reveal diversity among visitors from other stellar systems. They test whether local experience predicts cosmic behavior. We have 3 confirmed interstellar visitors. 1. Oumuamua appeared inactive with mysterious acceleration. 2. Borisov showed conventional cometary behavior. 3. I-Atlas demonstrates extreme anomalies, including impossible activity levels and exotic chemistry. 3 objects, 3 completely different profiles. The sample size is tiny, but the diversity is striking. Interstellar objects don't conform to simple patterns. They span enormous range of properties and behaviors. This diversity challenges detection strategies. If we don't know what interstellar visitors look like, how do we find them? Current detection relies on recognizing unusual trajectories, objects moving too fast for solar system membership. But if chemistry or activity differs dramatically, additional signatures might exist that we're not searching for. It also complicates characterization planning. When new interstellar visitors are detected, what observations should be prioritized? If each object is unique, generic observation templates won't work. Strategies must adapt to individual target properties. 3. I-Atlas demonstrates the value of comprehensive multi-wavelength campaigns. Images alone don't tell the full story. Spectroscopy is essential. Different wavelength regimes reveal different information. Coordination among facilities maximizes science return. Future interstellar visitor studies will benefit from lessons learned observing 3i Atlas. What worked? What gaps existed? What should next time's observation campaigns include that we're missing this time? The answer likely includes dedicated spacecraft. Remote observation has limits. Direct sampling provides data impossible to obtain from Earth. Missions that intercept interstellar visitors, match velocities, deploy instruments that measure composition and structure up close would revolutionize understanding. 3I Atlas makes the case for such missions better than proposals possibly could. Here's an object we can't fully characterize remotely. Here are mysteries spectroscopy can't resolve. Here's what we'd learn if we could touch it, drill it, analyze samples in laboratories. The photographs are still being analyzed. Researchers are measuring coma dimensions precisely, calculating jet geometries, modeling color changes, comparing current appearance to earlier observations in quantitative detail. But even before detailed analysis completes, the visual differences are clear. 3I Atlas transformed during solar conjunction. The comet that emerged looks fundamentally different from the comet that disappeared behind solar glare weeks ago. Expanded coma indicating massive material release. New jets suggesting surface changes. Blue color revealing altered chemistry. Asymmetries hinting at possible structural modifications. Changes that standard cometary physics doesn't predict should occur at these distances and conditions. NASA's release of these images to the scientific community and public demonstrates the significance. These aren't routine comet observations. This is unusual enough to warrant immediate dissemination. Researchers worldwide need to see these data. Observation campaigns need to adjust based on what the photographs reveal. And the public deserves to see what an interstellar visitor looks like when it's actively surprising scientists, when it's doing things that textbooks say shouldn't happen, when it's forcing revision of frameworks built on centuries of comet studies. 3I Atlas continues outward. Every day it moves farther from perihelion. Every day solar heating weakens, yet activity remains enhanced. The comet refuses to follow the cooling trajectory models predict. How long will this continue? Will activity eventually decline as thermal physics demands? Or will 3I Atlas keep defying predictions, demonstrating that interstellar comets operate under rules we're only beginning to understand? The telescopes are watching. Images are being captured nightly. Spectroscopy is accumulating. And slowly, observation by observation, the truth about this visitor from another stellar system is being revealed. The photographs show a comet in transformation, a visitor behaving unlike anything our solar system produces, an object teaching us that the universe contains more diversity than local experience suggests. That formation around different stars creates different outcomes. That chemistry varies. That behavior we thought universal is actually local. And somewhere in these images, in the expanded coma and new jets and blue coloration and structural asymmetries, the answers wait. What is 3I Atlas? Where did it form? What processes drive its behavior? What does it teach us about stellar systems throughout the galaxy? The photographs are the beginning. The detailed analysis will take months. The full understanding might take years. But we're watching it happen. We're documenting an interstellar visitor in unprecedented detail. We're learning what objects from beyond look like when they enter our neighborhood and encounter our sun's radiation. Comment below. What discovery would blow your mind? Most fragmentation into multiple pieces, detection of entirely new chemical compounds, or continued impossible acceleration. Subscribe now, because these images are just the beginning. Every clear night brings new observations. Every week adds detail. And as 3I Atlas continues its journey outward, continues defying expectations, continues demonstrating that interstellar visitors are more than just distant cousins of local comets, we'll be here bringing you every update about what we're learning from this cosmic messenger. The photographs have arrived, the transformation is documented, and the mystery of 3I Atlas just deepened further. Because what those images show isn't just an active comet, it's an object that refuses to follow the rules. That breaks physics we thought we understood. That demonstrates the universe is stranger, more varied, more filled with unexpected phenomena than we imagine. The visitor from another star is still teaching. The lessons are still unfolding. And the photographs released by NASA are the latest chapter in a story that rewrites what we know about comets, about interstellar objects, about the incredible diversity of materials traveling through our galaxy.